Hello, everyone. I'm Hannah. You probably know me from other conferences, but I work for Governed by Toyota in technology and standards team. And I like Constexpr, so that's my personal hobby. And I'm going to talk about it. But first, we start with C++ History 101. Because to appreciate what Constexpr gave us, is important to know what was before. So C++ 19.8/03. Oh, what's happening here? Oh, something is happening with my slides, sorry. Yeah, okay. So you have vector, 42 elements, not one element of 42. You iterated with iterators. You needed to name it explicitly. There was no auto. So you needed to take two iterators, iterate it, print it. If you want something like compile time expression, you needed to use metaprogramming like macros. So let's have macros square of a, which is a times a, and then you need square of 5, which will calculate 5 times 5. But if you added like some constant like base size, there can be some problems, like 5 plus base size is suddenly evaluated like 5 plus base size times 5 plus base size, which is wrong. It's not obvious for first, like when you look at it. So it's terrible, and I don't like using preprocessor for metaprogramming. But you can use templates even in C++ 98.03. You can create like a container for type, or you can have like storage of some size, because you can have also template parameters which are not types but values. But in order to store the size so it will be accessible from outside of the template instance, you need to create a name. And in C++ 98.03, you needed to use enum. It's terrible. And C++ 11, which is 14 years ago, we have auto. So you can initialize variables based on whatever you want. You can iterate range, you have range force. You can create Constexpr functions. So instead of preprocessor macros, you have real functions. And you just calculate it, and it's safe. It will evaluate it only once, and it's doing exactly what you want. But you cannot use any conditional statements, any like control for flow. So no cycles, no ifs. It's just one expression. So you need to be creative. You can use ternary operator. So if it's less than 0, evaluate it to 0. Otherwise, if it's 1, then evaluate it 1. And otherwise, you can do a recursion. And once you have recursion and conditions, you are template complete. So Constexpr in C++ 11 was template complete, but it was terrible to use. So you can also have static Constexpr variables inside of types, it's a little bit complicated. You can static assert on them, like it's just a name variable, like constant. You can give like error message, but you need to initialize it, define it outside of class, and that's terrible. Because it makes impossible to write nice templates or initialize it for any t. You actually needed to explicitly initialize or define every instantiation on your own outside of the class. This makes it really terrible to write any generic code, because you need to do it for int, unsigned. But also you have in C++ 11, you have lambdas. It's awesome. And they can have control flow, but sadly, they cannot be Constexpr. C++ 14, to make it a little bit short, you have template Constexpr variables. You still cannot define static Constexpr variables inside of structures, but you can use template Constexpr variables for that. So there is a like workaround. And there is a Constexpr function with control flows. You can suddenly have loops, ifs. It's much better word, it's much easier. Yeah, but it's still not enough. C++ 17 give you if Constexpr, which is not really an evaluation thing. It's more like template metaprogramming thing. It's really useful if you have template parameters for a function, and you can decide what you want based on any template parameter. And you can finally have Constexpr lambdas. C++20, and I'm not describing everything. C++20 give you memory allocations in Constexpr. That was a huge deal. We can finally have stat string, stat vector with caveats that you cannot return them outside of the Constexpr scope. You have also Constexpr virtual functions. And there is a Constexpr relaxation happen. We can finally, Constexpr became more like about its evaluation than its syntax. So if you had a branch inside of your code, and the branch contains something which is not Constexpr compatible, like at the time throwing exception or go to, it's fine. It's fine if it's not evaluated. That makes writing Constexpr code much easier. C++23 give us static Constexpr variables inside functions, which is good because you can reference them in template arguments, and they are not copied on your stack every time you call the function, which is super useful. And Jason Turner had a talk about it recently. I think I saw it in Code Dive, but he did it probably multiple times. There is multiple Constexpr relaxation. Constexpr became more and more about evaluation than about its syntax. And C++26 present, we can cast from and to void star if you have pointer, so we can drag a pointer to type arrays interface, which is useful to implementing function ref and a lot of types of polymorphism. We have Constexpr structure bindings, so you can create Constexpr structure binding on Constexpr variable, so you can access the pieces of it nicely. And there is many more features, but that's just like scope of things. And word of the day is caution. Constexpr was designed from the beginning by slowly adding stuff we were comfortable adding. At first, it was just expression because we already had expression in the language, in the enum. But then we added control flows because we became comfortable making control flow. But you can see that it's just once people get used to something, we will bring more. But Constexpr is actually a contract, not like contracts in C++, but contract with library user, if it's in front of function, obviously. It says that your function is able to be constant evaluated, and as an author, you won't break this promise. You won't use anything which will break this function to be Constexpr. At least in before C++ tried to make sure that every possible path is constant evaluatable. Current status in C++ since 23, I think, is that you can write Constexpr function which is not constant evaluatable anymore. So when it's evaluated, when you enter immediate context, there is multiple contexts where constant evaluation needs to happen. In static assert, in non-type template arguments, set array t expression. So if you calculate the expression, it needs to be evaluated as a constant expression. If you initialize or define a Constexpr variable, then it needs to be constant evaluated. If you calling constant eval function, and all its arguments are not are constant known. If they are not, the constant eval scope will grow, and it will eat your Constexpr functions from it, or otherwise it will give you error. And so look at this example, because if you look at the example, and please tell me in chat how many times function calculate size for is going to be called. Can you guess? Function, or how many times it will calculate some size? How many times function prepare storage will be called? Prepare storage will be called twice. and it will be called in this example in runtime, unless this code is in constant evaluated scope. But the function, it will be called twice in runtime, but function calculate size for will be called only once and during parsing of function prepare storage. Okay. So when you enter immediate context, also for instantiation, so if you have template Constexpr function in template, every time you instantiate the template function and the argument is depending on template argument, it will be evaluated. So during your compilation of your C++ program, there is multiple evaluation of constant evaluation, and it's running C++ program you wrote, but every time you it's called, every time it's evaluated, it's standalone instantiation, which doesn't know anything about other universe. It doesn't know about anything after the part you parsed, and it doesn't know anything about any other evaluation. There is no state. It's always just evaluation which will fold into one value. With reflection, it will change a bit because you can instantiate new types, but that's unfortunate, but also useful. So how is Constexpr code evaluated? In the constant evaluator, which is part of the compiler, and in Clang, because I'm familiar with Clang, and so I'm going to talk about Clang, but I think all the compilers are implemented kind of similar way. There is a file expr_constant.cpp, which is C++ interpreter, in basically one file, and it has 17,000 lines of code. You can see it on GitHub. It's fun to read. And it evaluates C++ independent of your C++ CPU architecture. It's just interpreter, and it can change its behavior and give you different behavior based on types of float your architecture supports, but it's not that it's using floats of your architecture or your computer. It's using floats you tell it it's supposed to be used. So it's going to use same float for your target architecture. And also it's implemented for C++ abstract machine. So it doesn't allow to happen anything which is not defined in standard. And if there is any UB or anything which is like invalid expression or something, it's supposed to tell you and give you error. It's very strict, and it's like kind of like really like a really pedantic C++ machine for you. But implemented in all compilers mostly is it just walks over AST. So if you have like operator plus, binary operator, it has two branches, left and right. So it will evaluate a left, then it will evaluate a right, and then it will calculate plus operation. If it's like just literal, it will just do the calculation of plus. Otherwise, it can call a function, which is already resolved, but during parsing, this operator is then changed into call expression. So it's just walking AST. Everything is prepared for it, and it just like giving semantics to already existing AST, all the casts, all the calls, all the statements, condition, everything is already there. Okay, it does symbolic execution. So if you create integer in Constexpr, it's not integer per se, like 4 bytes or 8 bytes or like bits, but it's something else. If you create a pointer, it's something else. It's not just pointer to memory, it's symbolic pointer. If it's structure, it's not just like a random blob of memory representing your structure. It actually is something which represents the structure much more precisely. This allows the interpreter actually discover all UB like UB you run into or any violation, etc. So symbols representing integer values, you need floating points, you need arrays, you need structures, you need pointers and references. I'm going to tell you how a compiler sees them in order to understand how it's evaluated. So what's a value? It can be it's represented with type called AP value, which is arbitrary precision value I'm not sure exactly. And it can be multiple types. It can be nothing, just initialized. It can be int, which is just store integer of arbitrary precision. You can ask it for integer of 256 bits if you want. You can have float of arbitrary precision. You can have array of other AP values. You can have union of AP value or AP value or AP value indexed by type, which is in union, or indexed by union member. You can have structure, or you can have you can have pointer. Sorry, so, and how do you like describing integers and floats? It's kind of obvious, but how do you like describe symbolically array? Inside of the AP value, you have three members: data, size, and capacity, and you create capacity 12 in this case. You create array of AP values. You point at the array, which is just C++ program. This is just all implemented in C++. And you can store other AP values in it. And they can be even different types. It doesn't need to be int. It can be float. It can be mixed. It doesn't care. But C++ has only like one type. Union is represented by having AST of the union, and then you have. I'm sorry, something happened again. Okay, union. You have AST of the union, and there is two elements: union of like field and value, and field is pointer to AST. So in this case, I have integer of value 0, and if I set it to something else, it's suddenly another integer from union and different value. These two are different objects, and so the interpreter actually tracks lifetime of your objects and lifetime of each member. And if you touch something which is not initialized, if you touch block union member, it will give you error because it's not defined. It can be float, it can be structure. And a structure is defined of value kind struct, and you have like multiple structures. And let me do this. Yeah, okay. You have structure, which is data, basis, and number of members. And for this structure, it has only, we have a circle, which has a parent position. So we have one base. And also we have three members: float, color, and color. And data pointer, it points to array of AP values, where first is base of the position, which is just another struct inside. Then there is a float, and there are two another structures as members. That's all. And from the structure itself, there is another structure with two floats. With the another structure is another structure, etc., etc. And pointer is the most complicated type to represent, and actually the hardest, because you cannot represent others. Because if you represent others, you can access anything, and then you cannot actually detect if you touch something you are not supposed to. So it's a little bit more complicated. You have object you like point at, and then you cannot use the others, obviously. So you need to use AST location, how the object was created. So you can point at null, obviously. You can point at initialized object. You can point at object, initialized one, or you can point at array on multiple members of each members of the array. Or you can also point past the array. You can point past any object, because any object can be represented as a range. And but there are no like numeric addresses. So like symbolic representation of pointers is actually much more closer to standard. They are not ordered. You can compare only pointers representing pointing to same base like object, which is common, and you cannot point to independent objects. So A and B, how do you like sort them? Oh, again, it happened again. Sorry. Yeah, pointer. Okay, ABC, and you cannot sort them. ABC, there's no sorting, and there can be multiple of them and multiple dimensions. It doesn't care. It doesn't matter, and you cannot sort them. So you shouldn't compare pointers which are not pointing at same base objects, an array. And for that, it's like really useful to understand pointer provenance. You probably heard this term, and it helps you understand what you can reach from with a pointer. So you have structure of some x, y, z, and you have like some array, AP value representing the array. You have another structure of items which contains array and count. But this wouldn't work because you can point past the array and count, and it's not the same object, so you need to represent it a little bit differently. So actually, arrays are sub-objects. You need to think about like original object is having only 2 members, and the array itself is another object inside. And then you have another object on top of that. This is just example. And then you have pointer to the object. That's the object you allocated on stack or heap, whatever, it doesn't matter. But if you take a pointer to a member, you can take pointer to first member of the top object, represented with path.0. And then you can, from there, you can go only down to objects inside of the object you are representing. In arrays, you can also go to neighbors, siblings, and always you can go down. And from in the arrays, you can go to the left, to the right. You can go past. So it's basically an object you allocated, some name, symbol, A here, and some path. How do you get there? And you can always go only down, and in arrays to siblings. So that's how compiler, at least Clang, represent a path. I would actually be interested how MSVC does that. But yeah, I will ask probably out someone later. L value and R value. Do we need to represent L value and R value? One is on left, one is on right. It doesn't matter because it has values, and it's more like property of type, not of the value. R value just means it's marked as a temporary, and you can steal it, but so it's property of C++, not actually values. And R value represent lifetime, so I have like lifetime of global variables, scope-based, lifetime temporaries, and custom heap allocations, which actually can go forever. But if you won't clean after yourself, your program won't be valid constant evaluation because you cannot leak anything. Temporaries can be lifetime extent into scope-based or global-based. So for pointers, identifier of the object is its location in AST. So global variables are identified by its name, AST node, for example. Local variables are identified by AST node and version. So every time you call a function and you get a pointer to local variable, and maybe you return the pointer to local variable, the pointer cannot be used again if you call the function again, like if you leave it. So you need to make sure you can check. So compiler needs to do that. So there is a AST node and version of call. So every time you go into the function, enter it, version is incremented. And if your version is not matching with function, it cannot work. Allocation values, dynamic allocations, are identified by unique keys. Because you allocate them and only it's just unique key. So it's actually like a key which increments 0, 1, 2, 3, 4, 5, and it goes kind of forever. So pointer is actually a p-value if we have structure of coordinates and some function. So it contains this thing we are going to point at contains 2 values, and we point at it. So the pointer is containing the pointer to AST at the actual definition of the variable declaration. Version because it's local variable. And then if you enter again to function, it's other version, the version, etc., etc., etc. And you can also go into submember. So you need path, which is represented as an array of numbers. In this case, it's path to first member, hence 0. Yeah. So if you have pointer to allocation, dynamic allocation, you have the pointer to expression where it's originated, its key. From the expression, you can deduce type. So a compiler can compare types. So if you have pointer and you try to access it something else, it won't work because it knows the original type. That's how void star cast there and back works. And you have just some key which represent the allocation. You can have obviously pointer to sub-object, and then you need provenance and multiple path, and it's a little bit more like. So if you have like a lot of sub-object in Clang, you will get a long path, and it's and the path actually itself is allocation. So if you want to be, if you want to have a fast Constexpr program, you shouldn't use many sub-objects, but don't do that. Use sub-object; it's nicer. Okay. So, what if you have like a global object? So I pointer to global object into AST, and the value itself is actually inside of it, because AST itself contains the AP value of the object, because global objects, static Constexpr variables or static variables are dragged into runtime and emitted into code. So where are the values stored? Global variables in the AST node, local variables in a stack-like data structure. Allocations are in just.map. And there is a question. If compiler authors designed a machine to interpret C++, should all standard library be constant evaluatable? It's like important question. And so let's look at the containers in standard library in C++ 26. Array is Constexpr since 11. Degu is since 26. Flatmap since 26. Flatset since 26. Forward list, same. In-place vector, same. Hive. Sorry, when I was writing the paper, Hive wasn't in draft, so we need to fix that. List, Constexpr, map, optional, set, basic string, another map. Everything is val array, not val array. And vector, everything is Constexpr mostly. So once the interpret is strong enough, and already it's strong enough, we can represent most of the C++ to be evaluated in Constexpr, in constant evaluation. So let's look at the some containers, how they work in detail, but just for fun. So we have stat array, you have object, you have index them, and you need to initialize them. They must be like they can be initialized, and uninitialized value are not allowed. In 23, in 26 they are now allowed with union trick. So we can have iterators back in end. We can have another iterator. We can iterate over the array with provenance. It's allowed because it's just array. We can modify it because it's just object, and it was work. It's working just easily. So that's the array. We can do that. We can then when it's destroyed, it destroys its members from back. So they behave same as stack variables. So you create like first in, first out, last in. Yeah, it's just like stack. So vector is 3 members, data size, capacity. We can create members. We can move them, but if there is an exception, tables like we cannot do that if there is exception during moving. So we actually need to copy it, and then we can copy it safely, then release it. And every time we use like vector and we need more capacity, it's usually like instantiated the allocation with twice more capacity. Some implementation do some different values, but I think like there is like they measure it some number. It's like 1.6 something, but Clang and GCC is doing ×2. So obviously, if you have pointers and you allocate and you create new allocation, iterators will be broken. They cannot reference something which is no longer there, and interpreter can detect that because you iterator internally contain pointer, and the pointer will point at something which is no longer existing, and representation of the pointer in the interpreter allows to detect it without crashing. So you need to move them, and then you have like destroy them from the front. Vector is actually destroying elements from the front, not from the back. That's important. And then you can grow more and continue. And you can have iterators, you can erase element. So you need to move everything and then shorter size, and you have some capacity still there. You can destroy multiple elements, and it's still all an algorithm based on the number of elements you need to move. There, yeah, and it's destroyed from the beginning again. List is similar. Like you have list, you have like front, back, and every time you create, you need to allocate. So it's not effective data structure, but it's just allocation and it works, and there is no reason why it cannot be Constexpr, and it's not now. It is. So you can have iterator. Iterator is stable when you modify it, or you can pop it. It's O1 operation. You can have iterator in the middle. You can destroy something in the middle, delete it, and then it's deleted. It's safe. Iterator will be moved to the next element. You have in-place vector, which is based on the array. So you have capacity, content, and you have size, and you can put it there. But problem is, at least in C++ 26 until recent meeting, you couldn't let in Constexpr initialize members in array on stack because in-place vector is on stack. So in-place vector for non-default initialized type couldn't be Constexpr. Now we fixed that in the meeting, so it's fine. So you have in-place vector also. Constexpr, you can have deque, which is just like a kind of like vector of leaves, which is like cute data structure, but people don't use it. And it was actually inserted into standard kind of as joke with intention that it will never get into, but it's stuck and it's there. But there is technically no reason why everything shouldn't be Constexpr. Kinda. We have control flow if for a while we have variables. Since C++ working, we can call lambdas in Constexpr. We have trivial default initialization, so you cannot you don't need to initialize every Constexpr like every variable inside of console-related code. You can have try catch since 20, but not like throwing exception. You can change active member of union. It's also C++ 20. Before that, you needed to actually destroy whole union and initialize it from fresh in order to make it work. You can have inline assembly, but you cannot evaluate it. You can have virtual function in Constexpr C++20. You can have Constexpr unique pointer since 23. You can have atomic operations like stat atomic of int or stat atomic of pointers since 26. You can have exception throwing since 26. So you can actually throw exception out of like Constexpr function and catch it, and it's fine. If you throw it and won't catch it, compiler will tell you that it's no longer valid program because if you need to be in Constexpr constant-related code, all allocation needs to be reallocated and all exception needs to be thrown. If they are not thrown, compiler can use the error message from .wat member of the exception and print nice error message. You can have trivial unions. So you can have an array of initialized members, and it can be contiguous. That was the biggest problem with the in-place vector. 26. We can have virtual bases tentatively in 26. So in future, we can make IO streams, string stream also Constexpr. We can have Constexpr share pointer tentatively in 26. Hopefully this Friday it will go to a library wording review. Coroutines tentatively since 29. It passed twice evolution and it's now in core for 29. It's kind of hard to implement them, but it's useful. Can you use byte arrays as object storage? Not yet, because everything is interpreted as symbols. So you cannot have arrays of bytes and just cast it into something else and hope for the best. Okay, so and then pointer tagging. So yeah, oh, I'm going over time. Sorry, I need to go faster. Pointer tagging, not yet. Reinterpret cast, not yet. So let's look at the wording. Constexpr and constant specifier tackle Constexpr. A function is Constexpr suitable if it's not coroutine, and if the function is constructor or destructor, and its class does not have any virtual base classes. Except for instantiated Constexpr functions, which means templated function, non-templated Constexpr functions shall be Constexpr suitable, which means you cannot write Constexpr function if it's coroutine or if it's a constructor or destructor of type which has virtual bases. Virtual bases are tentatively in 26, so function is Constexpr suitable only if it's not coroutine. So Constexpr is just a limit of execution, not syntax anymore, like with exception of the coroutines. Is still Constexpr in front of functions needed? That's a question for you to think about. This doesn't mean anything, because look at the constant expression, and expression E is a constant expression unless the evaluation of E following the rules of abstract machine into execution would evaluate on one of the following. There is a list of things which cannot be in order to be constant evaluation. So an invocation of non-Constexpr function. So if you call something which is not Constexpr marked, then it cannot work. If it's undefined Constexpr function, so you have only definition, declaration, but no definition, and instantiation of Constexpr function is not Constexpr suitable. That is not Constexpr suitable. So if every function will be Constexpr suitable once we have coroutines and virtual bases, then this point will be nothing. 10.4, you cannot call undefined function anyway. And non-Constexpr function, it's just one thing which will block us from calling a function which is not Constexpr. Just like this one line of standards. So Constexpr in front of function, not important anymore. It was a contract and opt-in into constant evaluation, which was defined by cautious. But now everything kind of be Constexpr, and this opt-in should be maybe just opt-out. In GCC and in Clang, there is a F implicit Constexpr, and I have PR for Clang, and I hope we'll get in, but keep fingers crossed. Then suddenly you are in a world where you don't need to write Constexpr in front of every function. So that's Constexpr everything. Sorry for going over time.
Thanks very much, Anna. So that this is another default that C++ got wrong. Then we should just everything should be Constexpr.
Exactly.